Okay, I think we'll get started. So today we're going to talk about the method of initial rates. And so last time we talked a little bit about kinetics in general, and we ended with the idea that there's going to be two distinct ways of getting the rate law, and one of these is the method of initial rates, and the other is the integrated rate law, which we'll talk about next time. So the best way to learn about method of initial rates is to do some examples. So I'm going to do two examples here to show you two different ways the data might come at you, and then I'll kind of let you be on your own for this. It's just a matter of working through the problems in your book. Any book you have will have a number of problems on method of initial rates in its kinetics chapters. All right, so let's imagine we have this reaction, and this is an overall reaction. Because, well, it's an overall reaction, so therefore we cannot get the rate law directly from the stoichiometry. So we have to systematically do experiments to fish out the rate law. In the experiment, we're going to have one more run than we have reactants. So in this case, we have two different reactants, A and B, so we'll have 3 runs. In the first reactant, we just choose some starting amounts. I've chosen these. We're in control, so we can control the amounts, so they don't have to be equal, just they need to be some known value to you. And what we're going to do is continuously monitor A, is watch A until it reaches 95% of its initial value, so a 5% drop. That's where the initial comes in initial rates. We're only looking at the first few percent of the reaction. So essentially what we're going to do is start our reaction, start a stopwatch, and then time how long it takes for 5% of the A to drop. So in this case, let's say these are the data. Data are right here. So these are the data that we'd be given or recording in the laboratory. And then we have to do some calculations. So this is the 5% of the drop. And then this is our initial amount here. This is this. And so we do this over the 10 minutes and we get a rate. Now, this is in moles per liter. And it's a concentration, moles per liter, per minute. Or same thing here, molarity per minute. Those are both the same units there. All right. Then in the second run, we keep A the same and double B. And then we record the time. And then we calculate our rate. And then finally in the third experiment, we double A and record the time and do our calculation. Now what we do is we compare these initial rates. So when we compare the first experiment to the second experiment, we see an increase, a doubling of the rate. And then we ask ourselves, what did we do? We doubled B. So doubling B doubled the rate. So the concentration dependence here is linear. So from this here, we would get NB equals 1. The order of B is 1. Now let's compare the first to the third. In this case, we put B back to where it was, but doubled A, and our reaction quadrupled. So now we're quadratic in the concentration. So NA equals 2 here. So we can get the final rate law based on this method of initial rates here. All right, let's do one more example so that you can see a different way these data come at you. So here are the data, calculations on this side. Same kind of deal. Now we've got 3 reactants, so we're going to run 4 experiments, or 4 runs of the same experiment. And then the runs are going to differ by just simply changing one of these at a time. So we're going to double from the initial reaction number 1 at a time, these reactants. Now, instead of using a stopwatch, what we're going to do is set a timer, let's say for 1 minute. And at that 1 minute mark, we're going to measure how much concentration of A we have left. And so in this example here, in the first run, we start with 0.1 molar, and then after 1 minute, we have 0.095 molar. So we've had a very small drop. So you want to choose the time here so that the drop is small. We're still under the conditions of initial rates. We do this calculation, and we get our rates. In this particular case, if we double C, we get a doubling of the rate. So N sub C here is 1. Therefore, we should be linear in 1. Here's an interesting one. For B, the rate didn't change. And so in this case, N sub B equals 0. So we're picking out a 0th order behavior for B. And then here we see a quadrupling. So N sub A equals 2. We doubled A in this case, and we got 4 times the rate of the reaction. So we end up with no dependence on B, B to the 0, and second order in A, first order in C. Now, this method of initial rates is good for most reactions of this type. It is it's not going to really work well for feedback reactions and reactions that have non-power law rate laws. But it will work pretty well for these types of reactions. Another thing where it wouldn't work so well is when the initial rate is not a good representation of the overall reaction. So some reactions have what are called induction periods, which is sort of a slow start, and then they get into more of a cruising speed for the reaction. Method of initial rates will not capture the correct behavior for those types of reactions. But for general reactions that we usually see in general chemistry laboratories and so on, this works pretty well. So again, you'll have a lot of problems in your book that you can work on there, and I encourage you to do that. Let's just pause for a minute and talk about the units. We talked a little bit about units here. These units are going to be the velocity of the reaction. So the velocity is always in moles per liter per time. Right? So it could be moles per liter per minute, per second, per hour, whatever. So whatever unit of time you're using in the reaction. In these examples, let's just take minutes. So if we're moles per liter per minute on this side, then this side has to be moles per liter per minute. And what we'll notice here is that K does not have set units. It depends on the order of the reaction. So let's look at a first order reaction here. Here's our moles per liter per minute for V. And then what do we got here? This is moles per liter. And so K has to contribute units of 1 over minutes. So in a first order reaction, K is just 1 over time. This is going to be the only case where K is independent of concentration. Let's see that in the case of second order reaction here. Moles per liter per minute, that never changes. That's our velocity. That's how we define our velocity. And so now here we have moles squared per liter squared. So K has to carry the per minute. So there's the per minute, 1 over minute. And then it has to cancel one of these liters and one of these moles. So it also has to have a 1 over concentration here. And then finally for third order, we get moles per liter per minute here. And now we're concentration cubed. So K has to carry a 1 over concentration squared, or broken down further, it would be liter squared, mole squared, per mole squared times minutes. And so what we see here is that the rate constant does not have consistent units across the different orders of the reaction. So it's order dependent what the units are. So you always want to be careful to understand the units of K when you're working with them. Little side bit here. This is called the method of isolation, and it's a good principle. It isn't directly going to give us the rate law, but it can be used in tandem with this technique or the integrated rate law technique to figure out the rate law. So let's give that a try. So let's go to this reaction. Again, this is an overall reaction, so we can't read the rate law from the stoichiometry. Here we're going to do just two experiments. The first experiment, we are going to set things up in the stoichiometric ratio. So here we see a 1 to 2. So whatever we choose for A, we're going to choose, in this case, twice that for B because of the stoichiometry. So we're setting up the concentrations such that we don't have excess reagent. Then we will somehow observe the order. Okay, and so what this means is that we're using some method, maybe the method of initial rates, very likely the method of integrated rate laws, which we'll talk about next time, but some other method, and we observe an order of 3. So the observed order is the observed order. Again, we can't. Why is it 3? We wouldn't see that from these data. That has to come from a separate experiment. Now, and so this will be our overall order. Because A and B are in stoichiometric amounts. Now what we're going to do is take one of these, in this case A, and swamp out B with it. So here we have way more A than we have B. So A is the massive excess. And so let's think about what's going to happen during this whole reaction, not just the initial part, but the whole reaction. This reaction is going to end, let's say it's very favorable, so it comes all the way this way. So in the case, let's take the extreme case where it goes all the way over. If it goes all the way over, we have 1.00 molar. B will be completely gone. Right? So if this is gone, that's going to chew up only 0.1 molar of A. And so the final concentration of A is going to be 0.99, which is approximately 1. So A is constant throughout the reaction. And that's where the name method of isolation comes in. We're isolating the limiting reagent here because we have massive excess of the excess reagent. Its concentration is not changing appreciably across the reaction. And so then, let's look at a rate law here. This guy's constant. So this whole thing is constant. This is not constant. And so that's going to isolate NB. And so when we observe an order, this is going to give us just NB. Because this has not changed during the reaction, this is controlling the rate of the reaction. And so it would say it would be the order of B. And so we have an overall order of 3. We have an order of 1 for B, and so therefore our order of A is 2. And our reaction rate law would be K A squared B. So this is one other technique that might be necessary, not always, maybe even not often, but this is the method of isolation. It brings back some of the ideas about limiting reagent and excess reagent, so it's a good problem to think about. I'm not sure your book will have, probably have a couple of problems on this, depends on your book. This is less important in the grand scheme of things than fully understanding method of initial rates. So practice that, and then next time we will look at integrated rate laws, which will involve a little bit of calculus, but we'll just walk through that slowly.